Right, I think we can start this afternoon session. So we're very happy to have Nathan Berkovits, who's going to speak about manifest spacetime supersymmetry and the superstring. Thank you very much.
Okay, thanks very much for the invitation, and I'm sorry I couldn't be there in person. I'm going to be talking about a paper I wrote a few months ago called Manifest Spacetime Supersymmetry and the Superstring. So there are various motivations. The main motivation is to try to really understand the relation between what's called the Rns Formalism formalism for the superstring and the pure spinor formalism. And of course, the Ramon-Niver-Schwarz formalism is much better understood, but space-time supersymmetry is not manifest, so it has some problems. And pure spinor formalism, at least computationally, is much more efficient. People have computed up to 3-loop superstring computations using the formalism. But there's still some mysteries and trying to understand, there's some subtleties in the multi-loop formalism. And hopefully, by understanding the relation better between the two formalisms, that will be useful for trying to understand these subtleties better. So, of course, the Rns formalism has manifest worldsheet supersymmetry, and it does have d equals 10 spacetime supersymmetry, but it's hidden or not manifest. That makes it difficult not only to compute scattering amplitudes because there are cancellations coming from supersymmetry, but even to describe Ramon-Ramon backgrounds, which of course are necessary if you want to describe anti-de Sitter space. So the pure spinor formalism is in some senses the opposite. So the spacetime supersymmetry is manifest, but the local worldsheet supersymmetries, although they're present through a BRST operator, they're hidden. They're certainly not manifest. And the cancellations from the supersymmetry are manifest, but as I said, there's some subtleties coming in multi-loop, which, although there are some tools for trying to deal with them, certainly they're not well understood. So going beyond 3 loops, so what has been computed up to now has been 3-loop computations using the pure spinor, just the first term, so the term at low energies. Going beyond that to get the full 3-loop amplitude is still an open problem. And of course, in RNS, one has only been up to go up to 2-loop. So, so although pure spinor form is more powerful, one would like to even do better. So what I'm going to discuss here is a generalization of the Ramon-Niver-Schwarz formalism, which has manifest spacetime supersymmetry. And the idea is that this generalization is going to be somehow some intermediate formalism between the RNS and the pure spinor formalism. And hopefully will help not only to understand better the RNS formalism, but also to understand better the pure spinor formalism and these subtleties. So please interrupt me. So the sound system is very good. So congratulations. I think doing a hybrid conference is very difficult. And so please interrupt me whenever you want with questions. You don't have to raise your hand. Okay, so let me start by just reviewing the different formalisms. So the RNS formalism, of course, we have X's and psi's, and we also have the BC and beta gamma ghosts. And Ramon-Niver-Schwarz sectors are when the psi's are either have periodic boundary conditions or anti-periodic boundary conditions. So the BRST operator is a standard BRST operator, which you can write for any n equals 1 superconformal field theory. And in a flat background, it just has the form here. And then the gluon and gluino vertex operator. The gluon vertex operator, essentially, you can just read off from the BRST operator. Just essentially, it tells you how. So, for example, dx is just a translation operator, and psi is related to the Lorentz generator. But the gluino vertex operator is, of course, much more complicated. So in the RNS formalism, the Niver-Schwarz sector is very simple to describe. It just essentially comes from n equals 1 superconformal field theory. But to discuss the Ramon sector or the space-time fermions, you need to bosonize the ghosts. So this was done by Frieden, Martinek, Schenker 15 years after the formalism was developed. So you have the beta gamma ghosts here. which we're going to fermionize. So these are bosonic ghosts, but we're going to fermionize them by writing them as in terms of these 8n psi fields, which are free fermions, and this chiral boson phi. And then the spin field here, so this is a space-time spinor, and you can explicitly construct it by bosonizing the 10 psis into 5, so you split them up into 5 complex pairs, and then you bosonize them. And essentially you construct the spin field out of these chiral bosons sigma. So the Gluino vertex operator is much more complicated than the gluon vertex operator, and that makes it difficult to describe Ramon-Ramon backgrounds, because the gluon vertex operator, the ghosts and matter fields essentially decouple, but in the Gluino they couple just because you have to bosonize all these ghosts here. So, of course, space-time supersymmetry is also not manifest just because the Neveu-Schwarz and Ramon sectors are, of course, related by space-time supersymmetry, but the vertex operators have such a different form that it's difficult to see how to make space-time supersymmetry manifest. Okay, in the 80s, it was developed Green-Schwarz formulas, which I'll call Green-Schwarz-Siegel, because he played an important role in describing this kappa symmetry. And also, the way I'm going to describe it, I'm going to use a first-order form for the theta. So we have the conjugate momentum to theta, which I'll call P alpha. So theta and P, of course, are now space-time spinors and worldsheet fermions. So I guess sorry, I said it wrong. They're space-time spinors, but theta is going to be a worldsheet scalar, and P alpha is going to be a worldsheet vector, if you like. The x's, of course, are worldsheet scalars. And Green-Schwarz, they weren't able to covariantly quantize, but of course you can introduce a BC ghost if you want. And the BRST operator that one can construct is constructed essentially from the x's and thetas. You can construct this space-time supersymmetric form of x and theta, which is invariant under the space-time supersymmetry. So the space-time supersymmetries are just here, it's just delta theta is just shifted by a constant, and delta x is shifted by that amount, just like usual 10-dimensional space-time supersymmetry. And the space-time supersymmetry generator can be written as this Q alpha. So Q alpha, of course, commutes with all the space-time supersymmetric objects. So another space-time supersymmetric object, which is convenient to define, is this D alpha. So D alpha is constructed from the canonical conjugate to theta. So the canonical conjugate to theta I'll call P alpha, so that plays the role of DD theta. And then small d alpha is something like the covariant derivative. So if you're thinking in superspace, you would write something like capital D alpha is equal to DD theta plus theta gamma alpha TDXM. So the worldsheet version of this is this small d alpha, just because dx here plays the role of ddx. And this satisfies a commutation algebra, which is if you take the Poisson bracket of d alpha with itself, you get something which is non-zero, which is just pi m. So that's the space-time supersymmetric version of x. That means that small d alpha has both first-class and second-class constraints. So pi is not the first-class constraint, but pi squared is the first-class constraint. So that means that small d alpha has first-class and second-class constraints, which we can quantize in light cone gauge. But covariant quantization of this theory is still an open problem. So although space-time supersymmetry is manifest, so all the BRST operator and the action is, of course, manifestly space-time supersymmetric, the BRST operator is not enough to quantize the theory. You also need these second-class constraints. Okay, now as I mentioned, you can also, of course, compute the anti-commutator of Q alpha with Q beta. That's also not zero. Of course, it's not supposed to be zero. It's supposed to generate the supersymmetry algebra. And in this case, Q alpha with Q beta generates the translation generator. Now that's different from in the Rns formalism. If you compute Q alpha in this description, one can also construct a Q alpha. So Q alpha is essentially just the zero mode of the Ramon vertex operator. So it's something like dz e to the minus phi over 2 sigma alpha chi alpha. Sorry, there's no chi alpha. That's a space-time supersymmetry generator, what's called in the minus a half picture. But as we'll see, Q alpha with Q beta in the Rns formalism is not the usual space-time supersymmetry generator. It's not equal to dx gamma m alpha beta dxm. That's essentially one way to see that space-time supersymmetry is not manifest. So that's essentially the disease we're going to cure in this generalized RNS. But before doing that, let me say something about the pure spinor formalism. So the pure spinor formalism has similar variables to Green-Schwarz in the sense that it has this x and theta and the conjugate momentum to theta, but it also has these ghosts. So these are bosonic ghosts. So if you want, you can think of the bosonic ghosts as coming from gauge fixing this kappa symmetry. So here we had a symmetry coming from these d alphas. So the d alphas describe first and second class constraints. The first class constraints are usually called kappa symmetries, and you can think of the lambdas somehow being ghosts for these kappa symmetries. So that's why they're bosonic ghosts. But they satisfy a constraint, which is why they're called a pure spinor. So in 10 dimensions, a pure spinor is a spinor. So alpha is 1 to 16, 10 dimensions. But because lambda satisfies this constraint, only 11 of the 16 components of lambda are independent. So Cartan called this a pure spinor in 10 dimensions. Now the BRST operator in this formula is constructed from the pure spinor ghost times the constraint. So that's natural if you want to think of a BRST operator as being the ghost times the constraint. But the unusual feature is that D alpha is not the first class constraint. So normally to construct a BRST operator, you need first class constraints. And essentially the fact that this has second class constraint piece in it is essentially canceled by the fact that lambda is a pure spinor. So because of this pure spinor constraint, if you compute Q squared, you get lambda gamma m lambda times pi m. And because this is 0, that means that Q squared x equals 0. So that's essentially the new feature of this pure spinor formalism. But the action is essentially the same as in the BRST operator, but you also have, of course, a contribution from the ghosts. So the action in a flat background in this formalism is just dx d bar x plus p alpha d bar theta alpha. And then there's a coupling of the w's with the lambdas. So w is the conjugate momentum to lambda of conformal weight 1. So these have conformal weight 0. And this has conformal weight 1. And the BRST operator, as I mentioned, is constructed from these fields. So lambda alpha, d alpha, remember, is defined in terms of these fields in this way. So it's the same definition as d alpha as we had in the Green-Schwarz-Siegel formalism. Oops, sorry. And the BRST operator and the action are, of course, manifestly space-time supersymmetric, using the same supersymmetry transformation as we had before. Now, in this formalism, the BRST operator is, of course, not the usual one. It doesn't have the BC ghosts, but you can still use it to define physical states. So you can ask, what's the cohomology of this operator? And you find it ghost number 1. It describes the usual, if we're just doing the open string. It describes the super Yang-Mills states, but now it does it in a way which is manifestly space-time supersymmetric. So it does it in superspace. So A alpha is a superfield, and you can gauge it to have the form where the lowest component is linear in theta, and that's just the gluon. And the term quadratic in theta is the gluino, and then the higher order terms are just derivatives of those. So this is called the super Yang-Mills spinor potential. And this would be the unintegrated version of the vertex operator, and the integrated version is what I call U. And that starts out with similar terms as in the RNS vertex operator, namely the gluon coupling is similar. It couples to dx, or more precisely the spacetime supersymmetric version of dx. And then you can also work out what the Gluon couplings are. So the vertex operators are relatively straightforward. Of course, they're all written in superspace. You can use these vertex operators to compute, as I mentioned, up to genus 3 amplitudes. Okay, so that's essentially a review. Of course, we can also do Ramon-Ramon vertex operators by taking the closed version of this, which is just you take the left-right product of two open string vertex operators. And that, by adding that to the flat action, you can just construct Ramon-Ramon backgrounds in a straightforward way. Okay, so that's essentially a review of these three formalisms. Before I go on to the next part, are there any questions? Okay, so now let me talk about how to make the Rns formalism manifestly spacetime supersymmetry. So as I mentioned, the usual supersymmetry algebra is this Q alpha with Q beta equals PM. And spacetime supersymmetry can be made manifest if the algebra closes without using equations of motion. So this is familiar to anybody who studies spacetime supersymmetric systems. So a simple example is, for example, just a scalar multiplet in 4 dimensions, so the Wess-Zumino multiplet. So it consists of a 4-dimensional complex scalar phi and phi bar, and then the spin 1/2 fields chi and chi bar. And if you just write the standard, let's just do free action first. So d4x. Now we're in 4 dimensions. Okay, so you have d4x, dm phi bar, plus chi. I'll write it using Pauli matrices, so you have something like this. So there's the free action. And you find that it is spacetime supersymmetric, and where these are the ways that phi and chi transform under spacetime supersymmetry. But you find that the algebra doesn't close without using equations of motion. You compute Q alpha with Q beta. So if you compute, well, I'm not going to try to do it. If you compute Q with Q bar on chi, you find that it closes only if you use the equations of motion d/chi equals 0. So the well-known way to solve that is to add auxiliary fields. So these f and f bar are scalar fields, which you add to the action just by adding the term ff bar. And now you find that the supersymmetry relations, if you include these terms in the spacetime supersymmetry variation of chi and f, you find that the algebra now closes without using equations of motion. And you can, of course, make spacetime supersymmetry manifest by combining phi and chi and f into a superfield. And then you can write this action as d4x, d4 theta, phi bar, so d squared theta bar, phi bar. Okay, and you can also, of course, add interactions by adding things like f of phi. So this is the usual f term plus complex term. So this is, of course, well known for anybody who studied 4-dimensional supersymmetry. And the key ingredient is adding these auxiliary variables. So in the Rns formalism, we try to do the same thing in the Rns formalism as I already mentioned. The spacetime supersymmetry generators have this simple form. It's essentially the fermionic vertex operator at 0 momentum. And when you take the anti-commutation, you find that you don't get dx. You get this object here, which is, you can think of it as the translation generator in the -1 picture. So in Rns formalism, one has this notion of picture. Which is essentially counting the dependence on this phi field. And more precisely, it's defined as d phi minus xi eta, where remember phi and xi eta are described here. So with this definition of picture, beta and gamma carry picture 0, but this carries picture -1 because there's an eta minus phi. And the way to get the way to relate this algebra with the supersymmetry algebra is to use picture raising. So to do that, we have to introduce this notion of what's called Hilbert's small and large Hilbert space. So the small and large Hilbert space is defined as states which are either independent, small Hilbert space is states which are independent of the zero mode of psi, and the large Hilbert space are the states which depend on psi. And physical vertex operators in the Rns formalism are essentially built out of the beta and gamma ghosts, which don't depend on the zero mode of psi. So they are defined in the small Hilbert space. So they're annihilated by not just the BRST operator, but by the zero mode of the eta ghost. Now, you can, in RNS, you can describe states which are in different pictures by hitting with what's called the picture raising operator, which is the BRST operator acting on the Xi0 mode. So this was, of course, discussed by Friedan, Martinek, and Schenker. And the reason why this is non-trivial is because in the small Hilbert space, the Xi0 mode is not allowed. Otherwise, this would, of course, be BRST trivial. So it turns out that this object here, which you get from the spacetime supersymmetry algebra, is related to the usual translation generator by picture changing. That means that you do this picture changing operation. Essentially, you multiply this by the Xi0 mode and take Q of it. And that's the picture raising operation, which takes this object into the translation generator. Now, picture changing involves this BRST operator, and BRST operator can only be defined, it's only, so picture changing is only a well-defined operation if all the states are on shell. So in other words, picture changing does not affect the scattering amplitude if all the states are on shell. So that's equivalent to saying the supersymmetry algebra requires equations of motion to close. So in that sense, we're in the same same situation as we had here before adding these auxiliary variables. So now what we're going to do is we're going to add some auxiliary variables to the Rns formalism in such a way that we remove this problem. So this is going to be a generalization of Rns, which is going to involve some additional variables. That's why it's called a generalization of Rns. And these additional variables are going to play the role of these auxiliary fields that we needed to make spacetime supersymmetry manifest. So before telling you what the different steps are, so we're going to need 4 different steps here to make spacetime supersymmetry manifest. First of all, we're going to have to work in the large Hilbert space, so the Hilbert space including the Xi0 mode. Then we're going to add these auxiliary variables. Then what we're going to do is just going to modify the spacetime supersymmetry generator by adding something which is BRST trivial. So that, of course, does nothing when it acts on shell states. And finally, we're going to perform a similarity transformation, which is going to relate this modified supersymmetry generator to the same supersymmetry generator we had in the Green-Schwarz-Siegel forms, which is the same as in the pure spinor. Okay, so let's do these 4 steps. Maybe before, are there any questions up to now?
I have a request, which is, could you use a darker color for annotating?
Yep. Thanks. So, any other questions?
Can you make this analogy? Can you spend a couple more minutes on the analogy, please, between the So I guess maybe what I'm not understanding is that in the 4D, the standard Westonino story that you had,
yep,
it's just purely classical, right? It's just a classical field.
Yep.
In the RNS, you kind of, well, you talk about Hilbert spaces, picture changing, and so on. So you're in the first quantized formalism. Well, maybe you just say a few words about this. I'm confused.
Yep. Well, I'm just going to discuss it here. So, of course, the Poisson brackets are the same thing as like the classical spacetime supersymmetry generators, right? When you talk about quantum effects, I guess what you're thinking if there's some kind of anomalies or something like that to the Poisson brackets. But I'm really just discussing the classical spacetime supersymmetry transformation, how they act on the Wilczek variables. So I don't think I'm discussing, so picture changing is, maybe we can discuss this in about 10 minutes after I discuss what these auxiliary variables are. So maybe things will be more straightforward then.
I think I was trying to get the component fields and so on, but.
So I'll tell you what. Let's wait. Let me just wait until I introduce the auxiliary variable. So this might be a good question to ask at the end also, but I hope you don't need to know this just to try to understand what's going on. So let me just say a little more about these 4 steps. Okay, so if we're in the large Hilbert space, then of course the BRST operator is not enough to define the cohomology. We need both, it has to be both annihilated by eta 0 and by QRNS if we're in the large Hilbert space. But one way to implement this in a large Hilbert space is to consider the cohomology of Q prime, which is equal to the difference of QRNS and eta 0. So if something has a fixed picture and it's annihilated by Q prime, then it has to be annihilated by both QRNS and eta 0. And it turns out if it has anything but infinite picture, so if it has, it can be a sum of different pictures. It doesn't have to just be in a fixed picture, but if it has a picture, if all the terms in the state have finite picture, then you can show that the cohomology of Q prime is actually equal to the small Hilbert space. Now, if you work in a large Hilbert space, then and using this Q prime, you can understand picture raising as a BRST trivial operation in this following sense. So if I start with a vertex operator in one picture, and I add to it Q prime of C times V, so the term QRNS, when it acts on this, just gives the picture raised version of V. Whereas the eta 0, when it acts on this, just gives you minus V. So this cancels this. Then we're left with the picture raised version of the vertex operator. So if we work in a large Hilbert space and modify the BRST operator to be the difference of these two, then the cohomology of Q prime is just the cohomology of states in a small Hilbert space. And I'm assuming that the picture is finite again. Are there any questions about that step? Okay, then the next step is to add auxiliary variables. So what we're going to do is we're going to add a set of fermions and bosons in such a way that they don't modify the cohomology. So this would be similar to adding the auxiliary variables F and F bar, which don't propagate. So the way you're going to modify the BRST operator is by adding this topological term here, lambda alpha p alpha. So this is the standard topological quartet mechanism, which tells you that physical states are independent of the thetas and p's and the capital lambdas and omegas. Any question?
So what's the nature of these auxiliary variables? They're not worldsheet fields.
Yes, they will be worldsheet variables. So the action, let me write it down. I have space. So the action will be the original action, it's called S0. So this is our SRNS. So let's just do the holomorphic version. So that's going to be omega d bar lambda. So in a flat background, they just have this ordinary first order action. Okay? So the holomorphic. Now, if you're doing type 2, of course, you'd also have the right moving version. Okay, and they appear in the BRST operator in this way. So of course, the term we added in the action, this term here, is actually BRST trivial. So you can write it as just Q of P squared C. So remember, the BRST operator had the term lambda alpha P alpha. So this, I guess you can write it as omega T bar theta. So you're adding a BRST trivial term to the action. Okay, any other question? Okay, so now we've added auxiliary variables. Now we're going to modify the space-time supersymmetry generator. So here was the original space-time supersymmetry generator. And now we're going to add Q prime of, I'll call it sigma alpha. So sigma alpha is just a combination of the variables I introduced. And of course, when acting on shell states, this term does nothing. So it's analogous to doing what we did for the four-dimensional case here, adding these additional red terms in the space-time supersymmetry transformations. Okay? So it modifies the space-time supersymmetry transformations, but in a way which doesn't affect on-shell states. So we're here. And now you can verify using these modified small q that the usual space-time supersymmetry algebra is satisfied. So what we've done is we've enlarged to the large Hilbert space. So now picture raising is a gauge transformation. Of course, using equations of motion, it's a gauge transformation. And then we've modified the space-time supersymmetry transformation in such a way that the on-shell transformations are, that on-shell states, nothing's changed. But now the algebra closes without using picture raising. So now you can try to make the theory manifest as space-time supersymmetric because the space-time supersymmetry algebra closes without using equations of motion. Finally, we're going to form a similarity transformation. So the similarity transformation is generated by this R. And that's also, of course, going to form the same similarity transformation on the BRST operator. But when you do it on this space-time supersymmetry generator, you find that it just takes the form of the Green-Schwarz-Siegel space-time supersymmetry generator. So now the space-time supersymmetry transformations are precisely the same as they were in the Green-Schwarz or in pure Spinor formalism. But of course, the BRST operators also changed. So after performing the similarity transformation, the BRST operator, which started out as being the Rns BRST operator plus this topological term, now has, of course, also a manifestly space-time supersymmetric form because it's now also going to, of course, commute with Q prime, with small q prime. So I call this modified Rns. So this is, of course, 0, which means that all the terms here are manifestly space-time supersymmetric. And you can work it out, and this is the form they have. So it has the usual Rns term, gamma psi m dxm, but of course now everything has space-time supersymmetry. It has some unusual terms. For example, it also has this term, psi e to the minus phi. Psi e to the minus phi, that's equal to 1 over gamma. So gamma was 8 e to the phi. So the inverse of that is psi e to the minus phi. So it's unusual, but it's manifestly space-time supersymmetric, and it's straightforward, for example, to write down vertex operators in the cohomology. And now, of course, you can write them in terms of the d equals 10 superfields. So these are the vertex operators. And so the vertex operator starts out similar to the unintegrated vertex operator. Remember, in the pure Spinor formalism, the unintegrated vertex operator, let me use red, was lambda alpha A alpha. So now it's capital lambda. I should have stressed this. Capital lambda is unconstrained. It's just a 16-component spinor, whereas small lambda is a pure spinor. So it does look a little bit like the pure Spinor formalism, but it also has a term which this term, of course, looks like the unintegrated vertex operator in the Rns form. Okay, and then you also have B and C dependence. The integrated vertex operator you obtain by essentially taking the term in the unintegrated, which is proportional to C. So this would be the integrated vertex operator. Okay, so one can check that this vertex operator, blue vertex operator, is in the cohomology of this modified Rns BRST operator. So it's manifestly space-time supersymmetric. If you look at how the gluon appears, so we're doing, of course, the open superstring. So this has the gluon and gluino if you're looking at the massless sector. So the Gluon vertex operator is not so different from the Rns vertex operator. So the Gluon vertex operator, you just look where the gluon appears in these superfields here. And you find that at lowest order in theta, of course, you have this term here. That's this term here. Then the terms proportional to C, you get a term here coming from here. And then the psi term comes from here. But now you get some additional terms. So these additional terms here involve the auxiliary variables. But they appear in a way which cancel in computations. That's just because essentially you have 16 capital lambdas, you have 16 thetas. And because these carry the same level, they essentially cancel because you have bosons and fermions which cancel when you do the OPEs. Now there are high order terms in thetas which will not contribute to the amplitudes, at least if you're looking at gluon tree amplitudes. That's just because there are no conjugate variables, so these small p's to cancel the thetas. So the gluon vertex, it's relatively straightforward to see that, at least for tree amplitudes, the amplitudes are the same as in the Rns formalism. Essentially, all the theta dependence just drops out, and this dependence here just gets canceled because of fermion and boson cancellation. Okay, but the gluino vertex operator is now very different. So the gluino vertex operator is, of course, the terms which have an odd number of thetas or are fermionic on the Wiltshire. So there's no spin fields anymore. And of course, I'm only discussing here the GSO projected sector. So I'm not, in the Rns formalism, of course, you can also have tachyons if you look at the GSO1 projected sector. So everything I'm saying here is just the GSO projected sector. And in that case, it's easy to see that everything is independent of the spin field. So I won't have time to discuss this, but if you want, you can also discuss, for example, what happens to the tachyon in this version of the Rns formalism. What you would find is that in order to describe the tachyon, you need to construct a spin field not out of the psi's, but a spin field out of the thetas. So the thetas would need to have unusual boundary conditions if you want to describe the tachyon. One way to see that is that you know that the tachyon is supposed to have square root cuts with the spacetime supersymmetry generator. Spacetime supersymmetry generator is now just essentially P plus dx slash theta. So the only way that's possible is if it has square root cuts with these variables. And once it has square root cuts with these, you also need square root cuts with these, just because in the BRST operator they come together. Okay, so that's a discussion of how we're going to make spacetime supersymmetry manifest in the Rns formalism. And then the next step is to relate this to the pure spinor formalism. But before I do that, now maybe I can go back to the questions that were asked about classical versus quantum. I don't know if you want to re-ask the question or if it became clearer now.
No, that's fine actually. No, it was just to think aloud. That's what I asked. Okay. So it's fine then.
Okay. So I mean, all of this is in the paper, but I'm happy to discuss and ask questions. Of course, we can do it at the end also. But are there any other questions about this? Okay. Okay, so now we have this formalism in which spacetime supersymmetry is manifest. The vertex operator for the Nivard-Schwarz sector is slightly more complicated. The vertex operator for the Ramon sector, I think, is much simpler than in the Rns formalism. But of course, what we want to do now is we want to use this to try to relate it to the pure spinor formalism. So in the Rns formalism, of course, we have fields which are half integer spin, which are these psi's and also the beta gamma ghosts. And that requires summing over spin structures. Whereas in the pure spinor formalism, all the fields have integer spin, which of course removes the need to sum over spin structures, which is why it's much simpler to do homogeneous computation. But now, if you want to relate the two, you have to do some kind of twisting because you somehow have to get rid of the half integer spin. And the way we're going to do this is we're going to twist the psi's into fermionic fields which have just integer spin. So of course, if we didn't have pure spinors, that would break Lorentz symmetry. So we have to choose 5 complex pairs of the psi's, which of course breaks the SO10 down to U5. But because we have the pure spinor essentially parameterizes how you break SO10 to U5. So with the help of the pure spinors, which I'll call lambda and lambda bar, so lambda is the pure spinor we had in the pure spinor formalism. Lambda bar, for the moment, let me just think of it as a constant spinor. When we do the non-minimal pure spinor formalism, it will turn out to be a dynamical variable. But at least in this talk, I want to restrict lambda bar to be constant just to simplify things. In the paper, I discussed the case in which it's a dynamical variable. Okay, so using lambda and lambda bar, so I'm going to assume that if you contract lambda with lambda bar, that's non-zero. And that's essentially related to a subtlety in the pure spinor formula. So lambda alpha, lambda bar alpha, I'm going to assume this is fixed and that it's chosen such that this contraction is non-zero. So of course, if I want to do this on the whole pure spinor space, I need to choose patches. So you can't do this globally on the pure spinor space, but you can do it locally in the sense that you can choose patches where for a fixed lambda bar, at least there's a set of lambda alphas or a patch of lambda alphas such that this is non-zero. Okay, so using lambda and lambda bar, I'm going to define how I twist my psi's. So these capital gammas will have a conformal weight 0 and capital gamma bars will have conformal weight 1. So that's just because of this, one is multiplied by gamma and the other is divided by gamma. So psi, of course, you can invert this to write psi in terms of the sum of capital gamma and capital gamma bar. And we're also going to decompose this auxiliary variable, capital lambda, into a pure spinor and an additional variable, which will be a vector. So lambda and u are bosonic variables. And you can show, I already mentioned that there are 11 independent components of the pure spinor. And 5 of the 10 components of this vector will appear if I contract it with gamma m lambda bar. So these 16 components can be used to decompose an unconstrained 10-dimensional spinor. Yes, question?
So by twisting, sorry.
Yes?
So by twisting, you just mean that you multiply psi with gamma.
Yep. So I'm not doing that. I haven't told you anything about the superconformal generators. It turns out that there is a way to understand, of course, the Rns formalism, before adding these auxiliary variables, had an n=1 superconformal generator. So find a place to write it. So we had G. And when you do this twisting, it's natural to think of this splitting into G plus and G minus. This is equal to dxm gamma m, and this is equal to dxm gamma bar m. But, I mean, this is a useful idea, but I'm not going to discuss this here, essentially, because after introducing the auxiliary variables, this n=1 superconformal generator is unclear. So remember, the BRST operator in this Rns formalism, after you generalize, it has a term, let me find it. Sorry, here it is. So it has a term here, which looks like it comes from an n=1 superconformal generator, but it also has this term. So it's not so clear how to describe the twisting in this language once we add these auxiliary variables. Okay, but in any case, in this case, I just mean by twisting, I mean just twisting the psi's into gamma and gamma bar and not discussing the superconformal generator. Okay, so what we've done now is we've introduced variables of just integer spin. So we've taken the size and split them up into fields of integer spin. And we've also taken the unconstrained bosonic spinor and split it up into a constrained bosonic spinor, a pure spinor, plus a vector. And now what happens is that after doing this twisting, only even powers of gamma appear. So assuming, of course, we're just talking about the GSO projected sector. Then after doing the twisting, essentially, since all the fields are integer except for the beta gamma ghosts, you know that the beta gamma ghosts also have to appear in integer combinations, which mean that only even powers of the gammas appear. So we're going to now define gamma hat to be equal to gamma squared. So of course, gamma had conformal weight minus a half. So gamma hat will have conformal weight minus 1. So now the ghosts, which I'll call beta hat and gamma hat, also carry integer spin. So they carry the same type of spin as the BC ghosts, but they have, of course, they're bosonic. Okay, so gamma hat has conformal weight minus 1 and beta hat plus 2. And I can also fermionize beta hat and gamma hat in the same way as I did before. And what you find is that there's a nice relation between the hatted eta and the Rns variables. So what you find is that eta hat, which is the fermionic, after it comes from fermionizing gamma hat, is just equal to lambda alpha, the pure spinor, times what we were calling Q alpha, just more precisely the BRST current, the spacetime supersymmetry current, which was e to the minus phi over 2 sigma alpha. So there's a simple relation between these hatted variables and the Rns variable. And now the final step is to just write the Rns BRST operator in terms of these twisted variables. And that's going to be related to the pure spinor BRST operator, at least after performing a similarity transformation. So what you have to do is you just take the BRST operator, so this BRST operator here. Sorry, I keep going too far. So here's the BRST operator. We're going to just use this, these twisted variables, which have integer spin, and write everything in terms of them. So in terms of the hatted ghosts and the gammas and gamma bars. And then what we find is we get something which is very similar to the pure spinor BRST operator after performing a similarity transformation. So R prime is this complicated similarity transformation, but after performing it, what you find is that the pure spinor and this vector that came from decomposing capital lambda, remember capital lambda was decomposed into small lambda nu, these separate into just lambda alpha times d alpha, and um just multiplies gamma bar m. So gamma bar m, remember, was just half of the size. So now what happens is that these fields decouple. So remember in the Rns formalism, the fields which decoupled, which had this topological term, were the thetas and the capital lambdas. In the pure spinor formalism, what you find is the fields which decouple are these u's and the twisted gammas, and also the ghosts. So remember now the BC ghosts and the beta hat gamma hat ghosts have the same conformal weight. They just have opposite statistics, and they also form this topological sector. So after doing this twisting and performing a similarity transformation, you just get back the pure spinor formalism, but now in terms of just the integer variable, the twisted variables. Okay, so that's essentially how to relate this Rns to the pure spinor formalism. And of course, when you do this twisting and writing the variables in terms of the integer spin, you find that the vertex operators we had before also reduce to the pure spinor vertex operators, plus of course something which is BRST trivial. So up to a BRST trivial operation, one finds that the vertex operators also map into each other. Okay, so this is what was done in this paper, and of course the next step is to try to compute scattering amplitudes. Okay, before I go to the next step, are there any other questions? Okay, so scattering amplitudes are more complicated because, of course, in the Rns formalism, we have this superconformal language of computing scattering amplitudes. In the pure spinor formalism, we do have a mechanism for computing scattering amplitudes, but it involves introducing regulators, which I'm happy to go into during the discussion session, but I don't want to talk about it yet. Okay, so let me just conclude, and then I'll say something about scattering amplitude. So manifest spacetime supersymmetry is, of course, useful for simplifying computations, and it seems to be necessary for describing Ramon-Ramon background. In the Rns formalism, the algebra closes only up to picture changing. But as I showed, by working in the large Hilbert space and adding auxiliary variables, you can get the supersymmetry algebra to close without picture changing. So this is not surprising in the sense that we do this all the time if we're working with field theories. Okay, now in this formalism, the vertex operators, at least for the GSO projected sector, can be written in superspace, so in terms of the usual 10-dimensional superfield. So this is, of course, very different from the Rns formalism. It turns out for GSO unprojected states, you can't do that. You have to introduce spin fields. But so in some sense, the Rns formula is more natural if you want to describe the Nevers-Schwarz sector, either in the GSO projected or unprojected sector. Whereas this description is much more natural if you want to describe both the Nevers-Schwarz and Ramon sectors, but also but only in the GSO projected sector, which is, of course, what we're interested in if we're doing supergravity. Okay, finally, after twisting this half-integer spin fields in this modified Rns formalism and defining this hatted ghosts as being the square of the unhatted ghosts, we were able to relate the formalism to the pure spinor description. Okay, so what are some possible applications? So, of course, one might want to describe Ramon-Ramon backgrounds using this modified description. So, of course, we know how to describe Ramon-Ramon backgrounds using the pure spinor formalism, but there's interest in trying to use this Rns description for describing Ramon-Ramon backgrounds, just because some things we understand better in Rns. So, of course, one can do this now because the Gluino vertex operator, or the Ramon vertex operator, and the Ramon-Ramon vertex operator, with just the left-right product of the Gluino vertex operator, no longer has spin fields. It no longer mixes the ghosts and matter fields. So it should be completely straightforward to write down now this description in Ramon-Ramon backgrounds. Okay, more ambitious thing one would like to do is to prove equivalence of the amplitude computation. So as I mentioned, if you're doing Nevers-Schwarz computations, at least tree amplitudes, it's completely straightforward to show equivalence. For Gluino, or for tree amplitude computations involving Ramon sector, it's not trivial even for tree amplitudes, just because the vertex operators are very different. But suppose we just stick to Nevers-Schwarz scattering. So at tree level, it's trivial to show that they're equivalent. What about at loop level? So as I mentioned, the vertex operators are very similar, but the objects that come in when you're doing homogeneous computations look different. But of course, this formalism, if it's correct, should be also be useful for showing the multi-loop equivalence. And there we see that there are different subtleties in the Rns formalism. So in the Rns formalism, we know that local Wolfschied supersymmetry means that you have to actually integrate over super Riemann surfaces, which involve both bosonic and fermionic moduli. And we know the integration over the fermionic moduli can be reproduced by introducing these picture raising operators, which are essentially the same operators we already discussed. And when all the states are on shell, then of course, moving these picture raising operators is a BRST trivial operation. But if you're doing homogeneous surfaces, although it's BRST trivial, it can contribute surface terms. And of course, taking account of these surface terms is a complication in RNS, but it's actually interesting and people know how to do it. But it's a subtlety in the sense that, the method for keeping track of these surface terms gets more and more complicated as you go to higher and higher genes. However, for certain types of amplitudes, you can show that these surface terms don't contribute. These are what's known as topological amplitudes, and they involve essentially scattering amplitudes where the amplitudes preserve a subset of the spacetime supersymmetry. So you can think of them as F terms. In the pure spinor formalism, there's similar subtleties. So I didn't discuss it, but if you work in these patches, it turns out that you need to be careful about when you go off the patch, what happens when lambda lambda bar equals 0. And it turns out that when you do multi-loop amplitudes, you have to work with operators which have explicit poles when lambda lambda bar equals 0. So such as this B ghost. And these poles cause subtleties. And again, in principle, one knows how to work with these subtleties, but life gets very complicated. And as I mentioned, for genus 3, it turns out that if you want to go beyond the low energy scattering of 4-point amplitudes, you need to take care of these subtleties. Now, somehow, if one could prove equivalence, these two types of subtleties must be, well, maybe they're not related to each other, but at least you should be able to relate the scattering amplitudes to each other. So you should be able to understand one subtlety using the different formalism. One clue that that's possible is that at least these divergences that come from poles when lambda lambda bar equals 0, they don't occur again for amplitudes which preserve a subset of the spacetime supersymmetry. So again, for these F terms, essentially, you don't have subtleties in the two formalisms. And that's a clue that there should be some relation between these subtleties. Okay, so that's the end of my talk. So I'm happy to stop for questions now.
Any question? So maybe I have a question, which is probably not really a question, but more of a curiosity. So do you think, is there a way, for example, to detect somehow from this kind of formalism something like, so for example, non-projectedness of the super moduli space, which is something that actually affects the computation of amplitude in the Rns formalism. So there might be a relation like this.
I'm sorry, so you were talking about the super moduli space of the Rns formalism? Is that what you're asking about?
Yeah, exactly. Like, well, we know that some issues, some difficulty arises in computation of amplitude in the Rns formalism due to the fact that the supermoduli space is non-split or non-projected. So I was wondering whether there is a you can actually see something like that, given that you can relate the Rns formalism to the superspace pure spinor formalism, if there's a way to see something like that, say, in the other part, in the other business.
Yeah, I think so. So that's essentially these subtleties that I was mentioning about. So one way to think about this non-splitness is these surface terms. So the point is that the relation of the integration over the fermionic moduli and the picture raising operators, if the space is split, then it's trivial to understand how to work with these picture raising operators. Whereas if it's non-split, then it turns out you need to be careful. You need to split the moduli space up into different regions, and the picture raising operators will be in different places when you do these when you split up into different regions. And there's the whole formalism that was worked out recently by Sen and Witten and how to glue these different regions together. And that's what I meant by these subtleties in the Rns formalism. So the hope is, yes, that these subtleties in the Rns formalism will be related to these subtleties in the pure spinor formalism coming from these poles when lambda lambda bar goes to 0. And I guess what I wanted to say is that for these topological amplitudes, for these F-term amplitudes, this splitness is not an issue. So, so there's certain amplitudes you can compute at higher genus, even infinite genus, at which you don't need to worry about the fact that the moduli space is not split. So I'm not claiming that I will be able to, in some sense, resolve the subtlety in the sense that there will always be this subtlety in Rns about the space being non-split. But I think this equivalence, at least you may be able to understand it in terms of a different language in which it comes from these poles when lambda bar goes to 0. So that's the hope. I don't know if I answered your question.
Yes, of course, absolutely. I mean, that would be very nice for me. I'm more into the, say, algebraic geometry part of this business, so I look at this problem from the supramoduli space point of view. So that would be awesome. Thank you very much.
Yeah, there was some paper. So there were some papers which I don't. So another way to try to answer your question, which I think has not been studied very much, is why in the Rns formalism these subtleties do not appear when the amplitudes preserve a subset of the spacetime supersymmetry. So there was some papers by Albert Schwartz talking about some kind of U5 description of Rns, which sounds like it has a similar flavor to what I'm discussing here. But again, I haven't been able to understand these papers, but it does have a similar flavor. So maybe you could try to study this directly in Rns also by seeing what it means when the spacetime, when the amplitude computation preserves a subset of the spacetime supersymmetry. So why that somehow helps.
Can I ask you another question about the intuitive understanding of this formalism that you described? So you call it a modified Rns formalism because you add these auxiliary variables somehow, right? Additional variables in the Rns formalism. You somehow you modify the BRST operators so that they don't contribute.
That's right.
And then you show that there is a different twist you can make so that you recover your spinor formalism.
That's right.
Is there, I mean, can you describe the way back, some way, let's say from the pure spinor formalism back to this modified Rns formalism?
Yeah. So to go back to the Rns formalism, you need to obviously introduce some new variables. So
start from the pure spinor formalism.
Let's suppose we start here. So here's the pure spinor formalism just starts with this lambda alpha d alpha here, just this term here. That was the pure spinor formalism. Now we're going to introduce, so the Rns formalism, of course, has some BC ghosts, right, and beta gamma ghosts. So we're going to have to add this topological set. And so instead of adding the theta lambda, now we're going to add these topological variables. So these are the original variables. And now we're going to add these auxiliary variables, which maybe you can think of as allowing the world sheet supersymmetry to be manifest. So in the opposite case, we wanted to make spacetime supersymmetry manifest. Here, in some sense, you want to make the world sheet supersymmetry manifest. So you can think of it in that way. I haven't thought about it yet, but maybe you could think of starting with pure spinor and then seeing what you need in order to make the world sheet supersymmetry manifest. And maybe that would land you on the Rns formalism. So I guess, yeah, you would have to just do the opposite twisting and try to construct these n equals 1 superconformal generators.
You don't have any picture chaining operators in the modified Rns?
So, sorry, so in the, so when you compute higher genus amplitudes in Rns, yes, you need to introduce picture changing operators in order to get essentially the correct picture for the higher genus scattering. Now, I didn't mention in the pure spinor formalism, what you have to introduce is this B ghost to compute higher loop amplitudes. And the B ghost, I think I wrote it down here somewhere. So the B ghost is this object here. I guess I didn't write it explicitly. It has these terms here which look very much like picture changing operators. So the picture changing operator in Rns was something like e to the phi psi m dxm. And this object here, if you write it in terms of the untwisted variables, pi is essentially like dx, and lambda bar gamma d is essentially like this e to the phi psi. So it does have a similar flavor. The B ghosts in the Rns form, in the pure spinor formalism, and the picture raising operators in Rns. So that's, of course, going to be necessary if we're going to have to relate the higher genus surfaces, higher genus amplitudes. I don't know if that was your question about how picture erasing comes in?
Yeah. Yeah, thanks.
Any other question?
Can you imagine, I don't know if that makes any sense, but imagine applications in sort of string field theory or for tachyon condensation or something like this? I mean, does this?
So yeah, tachyon condensation. So tachyons are much easier to describe using the Rns formalism. So if you want to describe tachyons in Ramond backgrounds, for example, there's a problem in any formalism. So in Rns, of course, the problem is to describe the Ramond background. In the pure spinor formalism, the problem is to describe the tachyon. So I think describing tachyons in Ramond backgrounds is maybe impossible to do. So tachyon condensation, I would say, no, that's probably RNS. You don't want to do pure spinors. But you can, of course, do other things with superstring field theory. So you could describe, for example, instanton solutions or things like that, where spacetime supersymmetry is useful. So string field theory in pure spinor formalism has some difficulties, mainly because of the pure spinors. So it's not, well, it's not difficult to describe the classical string field theory action, which is actually, Martin spoke a little bit about it. So you can write down an action of something like phi cube phi plus phi cube using the pure spinor field, using the pure spinor formalism. But if you want to quantize or gauge fix even, you need to describe something like this B ghost. And as I mentioned, the B ghost has these poles in lambda lambda bar, and that immediately starts to cause problems just because once you allow poles in lambda lambda bar, you have to decide how divergent the states can be in these poles.
I think it's even more complicated, Nathan, because it's not enough to have the B ghost. You need to do a full BV, consistent BV gauge fixing, which I don't know how to do yet.
Okay. So yeah, so I think we agree. So gauge fixing is complicated. It's not known how to do gauge fixing using the string field theory, but it's an interesting question.
Any further question? So if there are no further questions, I thank again the speaker.